So that is how you find the center of mass by hanging something. Now, because the center of mass always falls directly below the suspension point, gravity acts on an object equivalently as if the force of gravity were all focused at the center of mass. And this is why when we do universal gravitation problems, it's not the distance between the objects, it's the distance between the object centers. And in fact, it's the object centers of mass that matter, because it's as if all the forces act on that one point, and the center of mass is the critical point that we measure the distance between planetary bodies or large masses to figure out the force of gravity. Now, this center of mass has a lot of other applications. Again, we can pretend that all of the object is at the center of mass. We can pretend, even if it's a system of different objects that are moving in different directions, we can pretend that all the object's mass is at the center of mass. If you are trying to figure out the velocity of the center of mass of an object, if you just find the rate of change of position of the center of mass, that's all that is. And you can do that in a similar way. You just add up all the individual object, mi, vi, that's the momentum of object I, and then you divide that by v total, and that gives velocity of center of mass. So if you take the total mass of a system of many objects and then multiply that by its the velocity of the center of mass, even if the particles are moving in all different directions, you get the total momentum of the system. The whole system acts as if it were one object with its total mass, m total, at the position of the center of mass, moving with the velocity of the center of mass. And that can actually simplify a lot of problems for us. Now, very importantly, if there are no external forces on an object, this must be true, I should write this down here, and the center of mass of the system starts at rest. As long as there are no external forces, if that object starts from rest and its center of mass starts from rest, no matter what the individual particles in the object in the system do, the velocity of the center of mass will remain zero. So, for example, if we've got two people pulling on a rope and they're on skateboards, pulling on a rope on each other, okay, and I'm going to make this person a bit bigger, maybe a heavier person over here. They're pulling on that and they've got a bigger skateboard. Let's say the center of mass is right here. Let's say that is the cm in the x direction at this point right there. Now, even if they pull on each other and they end up over here, they're pulling on the rope and they end up, this person ends up over here and this person ends up over here. The center of mass will remain in the same position. This will still be the center of mass. Why? If there's no external forces, then the velocity of the center of mass will not change. It's as if the entire object is at the center of mass. If there's no forces on the system, like the entire object, the entire system of objects, then the center of mass will stay in the same position. And you can see that when two people actually do pull on these ropes and come closer to each other, the center of mass is motionless the entire time. And another example where the center of mass is useful is if there are many different forces, external forces on many different parts of a system, it is still true that you can still pretend that all the mass of an object is at the center of mass, and you just watch what that center of mass does. For example, if you have like 10 objects and they've all got different forces on them, it's true that the net external force will be the mass of the system times the acceleration of wherever that center of mass is. So even if the forces are on different objects, all you got to do is, if you want to find, you just add up all those forces, and that will be equal to the total mass of the system times the acceleration of the center of mass. Or another way to look at that, like Newton did, was the rate of change of the momentum. And if you are in the AP Physics 1 or 2 class, that would be, we'd use this situation, net force external equals, instead of dp dt, it would be delta p total over delta t. That is for AP1 and 2. So, but you can see it's very, very similar regardless. So this allows us to figure out what the entirety of a system is doing, how the center of mass is moving around, just based on all the forces on the individual particles, which can make a very difficult problem into a very simple one.